Good evening. On behalf of the Anandian Astronomical Association, it is my pleasure to welcome you to the second lecture of the Galileo Group lecture series. Today, we are honored to have with us our distinguished guest lecturer, Dr. Sibashish Laha, representing NASA, who has kindly agreed to deliver today's special lecture. I would like to express our sincere gratitude to Dr. Laha for accepting our invitation and for joining us to support and coordinate this island-wide lecture series. We are truly grateful for your time and commitment. I would also like to extend my special thanks to Dr. Anushka Udara, our first lecturer of the Galileo Group, for graciously agreeing to introduce Dr. Sibashish Laha to us. With great honor and respect, I now invite Dr. Anushka Udara to introduce today's guest lecturer. Over to you, sir.
Thank you, Lakiru. And thank you very much to the Anandian Astronomical Association for organizing this nationwide event and for inviting all these distinguished guest lecturers. It is my honor to introduce Dr. Shubhasis Lahar here. He earned his BSc from Presidency College, Calcutta, India, and also his PhD in astrophysics from Inter-University Center for Astronomy and Astrophysics in Pune. He is currently an associate research scientist at NASA Goddard Space Flight Center here in US. He has received numerous awards, including the NASA Exceptional Scientific Achievement Medal, the NASA Robert H. Goddard Award for Exceptional Achievement in Science, and the NASA GSFC Astrophysics Science Division Award. And more than that, he's a fellow of the Royal Astronomical Society. It is a very prestigious fellowship to earn. Dr. Laha is an invaluable supporter of the Sri Lankan astronomy community for the last several years. He has even served on PhD committees for the astronomy PhD program at the University of Colombo. So in addition to astrophysics, I would like to say that he's a good sitar player. If you want to learn how to play sitar, Shubhasis is another person that you can learn playing sitar. So thank you very much, Shubhasis, for your continued support. With that, take it away, Shubhas.
Thanks, Udara. Thanks very much for giving me this opportunity. I mean, it's can you hear me?
Yeah, loud and clear.
Perfect. So I'll just share my screen. I'll have a few videos to share, and please forgive me if I'm a little sloppy in this because Zoom is not allowed by NASA, and I'm working on NASA laptop, so I'm doing it from browser. So I think can you watch my screen?
Yes, sir.
Yes, so I'll need some response from you, otherwise I won't understand like what's going on in the background. So I guess this is a talk for mostly high school students and young graduates. So I have been speaking in public for many years now, and I have delivered lectures to school students, to university students, and I have as a definite set of ideas that I want to convey to you today, because lots of events that are happening right now at at NASA as a whole, and also in astrophysics in general in the world. And also I'll highlight some of my recent discoveries at the end, and I'll open up for questions. So yeah, so I work at NASA. I work as a mission support scientist, and I am so I actually joined a little late today because I was having an important meeting for how to maintain the spacecraft altitude of one of NASA's missions, and the sun is flaring a lot now, and that means that sun is throwing huge amount of high energy particles all over the space. And Earth is a very tiny thing in the solar system. I mean, by tiny, I mean literally a speck of dust compared to your size. When you compare the distance of sun to Earth and the Earth's circumference, but still the density of the particles thrown, it's called coronal mass ejection, is so high that it heats up the atmosphere, Earth's atmosphere, and the atmosphere level goes up. And what happens is that any spacecrafts that are going around the Earth in the low Earth orbit, we call it LEO, uh, they face more drag. So it's just like swimming in water. So if you're swimming in a very thick liquid, you have to put more force. And if you're swimming in water, your force needed to be less. And if you're like walking in air, that's just what you do, you need very little drag. So what happens is that solar flares push the spacecrafts down and also puffs up the atmosphere. So in all aspects, the spacecrafts um, are in a very problematic situation. So this is very common. It's not new, but there are ways to deal with it. So I was in that meeting, one of those meetings. So today, but I will talk about more into science, not about the spacecraft stuff. So I work on supermassive black holes and how black holes eat and how black holes gobble up matter and how AGNs, active galaxies, and high energy emissions come up and how galaxies evolve in in the cosmic timescales. Before that, I'll just I want to share with you something. Most of you have heard about the JWST, right? So the James Webb Space Telescope was launched in 2021 December, and it has been a huge success since then. And it has 52 deployables. I mean, by deployables, I mean you have to open up 52 times the 52 things, and all in space, automated. So it's a marvel of human engineering, and we are very glad that it's operating very well. And the region where the wavelength region where JWST operates is mostly in visible and infrared. And these are very important wavelength ranges to study many astrophysical things. And we have lots of telescopes already in place, but JWST is a game changer. So why do we need infrared, for example? So infrared is a wavelength which is a longer wavelength than X-rays, for example, like the wavelength is longer, but it's a very funny thing because infrared is so for example, our body is emitting in infrared in microwaves, and the wavelength that we are, so people have seen um, the movie called Predator, right? So in Predator, the alien predator actually observes in infrared as well, so they can see the heat signatures. So infrared is very important. Even when something is optically obscured, there is a thick obscurer in your line of sight, something which is not allowing optical photons to come out, but infrared in infrared wavelengths you can actually see them. So the interesting thing is that you can actually see stars forming from behind the dust. So I'll show you some beautiful pictures which JWST has taken. And just to give you a size comparison, JWST is way bigger than Hubble. And this honeycomb structure is very interesting because this structure naturally found in honeycombs. Of course, you have seen honeybees make this structure. These structures are very useful for compactness. So you can actually fold them, and you can fold them and deploy, and then unfold them, and you get this thing. So this is the way JWST was sent. Someone is drawing on my screen. Can that be stopped? So, so where is JWST? So that's a big question, right? So, I mean, these are all common knowledge given the fact that we have Google and now ChatGPT and Perplexity and lots of AI tools. But still, I want to highlight that this is an important journey that we had taken to put it at L2. L2 is so any two-body system has 5 stable points, gravitational stable points, which are called the Lagrange points. And out of those 5, certain Lagrange points, so L2, for example, here you see L2 is very, very interesting point because it's away from the sun, it's facing away from the sun. We don't want to face the sun because it's hot. And it's also like it's never occulted by the earth. So it's very far away from the earth. And it's away from the moon even. So and it is always observing, so it's never obscured by the earth. So for example, for low earth orbit satellites, sometimes it goes behind the earth and it's not able to observe that particular source. So you have limitations here. The limitation is 0. So this is something very important. And to send this spacecraft, it took a lot of fuel. As you can see, it drifted and took a lot of time as well. And now it's time for beautiful pictures. The things that I was telling you is that these stars that are getting formed in nebula, and stars form when huge amount of gas, dust cool and collapse due to its own gravity. So star is basically a ball of gas, but that gas cannot exist in itself, right? So why does that gas, like the sun, um, it's basically hydrogen and helium. Why is it so hot and why it's burning? It's because of fusion. Historically, people, like 200 years back, people thought that there are like coal that is burning, which when we think now it's ridiculous. There were different theories, and that's how science evolves. You propose a theory, you observe, you see that the theory does not answer your new observations, and you throw away the theory, and then you propose a new theory. So science evolved, and we understood that fusion is the most important thing. 4 hydrogen fuse to form a helium, and that is giving you the energy for the sun, for example, the stars. So nebula, why these nebula are very, very important for star formation is because they are rich places for gas and dust, dense gas and dust to collapse. They are cool, and they are like, I mean, I'm not getting into details of the physics, but there is a certain limit of mass that is required for the stars to form and then collapse due to its own gravity. And then once it falls due to its own gravity, the potential energy gets converted to kinetic energy that heats up to some temperature, and then it's very, very straightforward that the fusion reaction starts to happen. The same thing, the burst of the stars. So if you look at these pictures, I mean, not pictures, I would say, look at these nebula with Hubble Space Telescope, for example, or any optical telescope, you will not able to see the stars. You'll just able to see the nebula, and it's all dark and patchy. But you are able to see the stars within the nebula. You see these white stars within the nebula because you are looking at them in infrared, and that is very important. So one other thing is that you have seen the size of JWST, right? So the size is very big. It means that its collecting area is very, very, very large. And coupled with the fact that it's operating in infrared, it means longer wavelengths. So it can see very, very far in the universe. So you see that we are on the rightmost portion, 1.1 billion or a little more, and we can see a much much earlier black holes, and just when like the universe was born. And JWST has done a lot of such discoveries. I strongly recommend that you should go ahead and see all of these things. This is, for example, Saturn, captured with NIRCam, and so beautiful pictures with JWST. I mean, it's the rings are so bright and visible, and you can see that the rings are separated as well. And also you can see the the moons of Saturn. And again, like this is an active galaxy where you see a central black hole. You don't see the black hole, but you see that it's very bright at the center. So this is my topic of research. And this type of active galaxies are not very common, but there are lots of active galaxies in the nearby and the mid universe. And these active galaxies are perhaps the most important answers to the evolution of the universe, because these active galaxies have a black hole at the center which are actively accreting. Black holes don't just eat up matter. Why? Let me explain to you. So am I audible? Can someone say I'm audible?
Yeah, please.
Perfect. So why black hole does not directly eat you up? I mean, just for the sake of like the argument. The thing is, when you compress a mass to a certain radius such that even a photon cannot escape, so the escape velocity is infinite, then what happens is the black hole is formed. So I'll talk about that in a little detail later on. And black holes are the most compact objects in the universe, and when they feed in accretion disks, they emit a huge amount of radiation, which not just feeds but also throws. So my research is on like feeding and feedback of supermassive black holes, and these are also the nebula, which are beautiful pictures with lots of stars. You can see the infrared stars dotted within the nebula, which of course was not seen before. These are exoplanets transitions which JWST has discovered. I'm not getting into the details of these, but these are like some of the many great discoveries they have made. So this is a rare supernova that has been captured, and this is like a couple of galaxies having high T in the afternoon. So they are actually they are gravitationally bound, and they are getting into a gravitational collapsing structure. So they will have their own angular momentum around itself in the common center of mass, and then they'll eventually fall on each other, but it will take a long time. So Eta Carina Nebula is also something very beautiful. This is the deep field. There is a lensed galaxy in the front. So if there is a huge mass in the front, the lensing happens. I'll explain it later on. So you can see the lens. You see the curved things. So the background galaxy is the photons are coming, but it's coming in a lensed form. So I see multiple images of the same galaxy. Okay, now it's time for a video. Okay, so let me play the Artemis. So Artemis is something which is very, very hot news right now, because NASA is sending men and women to the moon. They will not land on the moon. Artemis 2 is to just go around the moon for 4 days, and they'll come back. So some few days back, the crew were here at Goddard, and the mission will be launched sometime around March. So we don't have a fixed date yet. Great. So I strongly recommend that you go and watch the news and keep a track on Artemis. The final destination will be Mars. So there will be the Artemis 3 program will be to land people on the moon, and Artemis 4 will be to have people land on Mars. So these are all long-term plans that we have here. Now, to get down to some mathematics, like I understand these are like very alien to you, but black holes are something which are also very interesting and alien to normal human conception. Because suppose you want to throw a ball from the surface of the earth, you throw it and it comes down. Why it comes down? Because the gravity pulls it back. Now, if you have a machine which can throw the ball at around a speed of, I don't know, like 11 or 12 meter per second, which is the escape velocity of Earth. I don't know the exact value, but this is something which comes to my mind. The ball will not return to the Earth. It will just go out of the Earth. Now, for Earth, the escape velocity is this. For Sun, the escape velocity will be very large. So it's obvious that it depends on the mass of the system. But is there a mass where the escape velocity is infinite, where you can't escape at all? Yes. The answer is yes. So what's happening? I'm not getting into the equation again. So Einstein wrote an equation where he combined space and time, and that's the brilliance of Einstein. And he found that there is an equation, there are certain times when a massive object can be compressed to the size of something tiny, so that the escape velocity is almost infinite. So what happens is, suppose you compress the earth, entire mass of the earth into a coin, whatever coin you have in your you use for transactions. If you compress the entire mass of earth into a coin, the earth will become a black hole. And what interesting thing is that if you place that black hole at the center of the earth, which is right now, and I mean the earth is compressed to that tiny teeny weeny part, the gravity will be the same, so the moon will still be in its place around the earth. So that's the funny part. So why black holes don't eat up things? It's because it's so tiny, but the gravity is far reaching. So although Einstein mathematically said black holes can exist, people were like Arthur Eddington said, nature cannot be so whimsical to create something which is inescapable. I mean, those things. And a young scientist who was very young that time, 21-year-old, I mean, most of you are of that age or less. So you guys have a huge potential in discovering new things. So think in a very profound and different way. So Chandrasekhar Subramanian was a young scientist from India. He calculated using quantum mechanics and gravity of Einstein's. He calculated that a star can become a black hole if it has a certain mass. So it will be a black hole if it is greater than 1.44 times the mass of the sun, for example. So sun will never become a black hole. Mind it, the gravity is not enough to compress it to a black hole. But if there is a star which is like 10 times the mass of the sun, 20 times the mass of the sun, 100 times the mass of the sun, definitely they have a chance to become a black hole. And believe it or not, we means the scientific community of the entire world, we collaborated together to get the first image of black hole in 2020. So this on the right, you see the image of black hole. So you can't see a black hole, right? Something which is absorbing everything, nothing can escape. You can't see it. By seeing it means the light from that system should reach your eye. If nothing is emitted from that system, how can you see that thing? So you have to see the shadow of that thing. So this is the black hole's shadow against the accretion disk. So how are black holes formed? This is a very important question. But before that, I want to show you a very nice video we made at Goddard some time back.
So you want to visit a black hole. You've packed your bags, you've updated your passport, and you're basically ready to jump on a spaceship and blast off. However, before you do that, I have just one piece of advice. Don't. Okay? If you really must go, I suppose you should at least know a few things about black holes before you leave. First, you should know exactly what a black hole is. A black hole is a physical object in space, just like everything else. It's made up of a tiny but massive point where gravity and density are infinite, a line beyond which everything, including light, can only fall into that tiny point, and sometimes some glowing stuff orbiting around it, and maybe some radiation. So basically, here is kind of bad, here is really bad, and here is safe. Also, black holes mostly come in two sizes. Don't ask me why, we still aren't sure. However, a black hole is also not a lot of things. It is not a hole, a cosmic vacuum cleaner, a portal to another dimension populated by unicorns and space potatoes, and absolutely not a good place to vacation. Okay, fine. I guess next you'll need to know how to find a black hole. Though technically black holes could just sneak up behind you, they likely won't. The nearest known one is 3,000 light years away anyway. However, if you were to go looking for one, there are a couple of good ways to find them. First, black holes tend to mess with their environment, so you can sometimes use interesting clues, such as a bunch of stuff orbiting what appears to be nothing. And second, as we mentioned before, there's often glowing stuff orbiting around them, caused by, well, when things get too close. So now that you've found a black hole and clearly aren't listening to me saying not to go, it's time for a few important safety considerations. First of all, the good news is that as long as you stay far away, black holes aren't that bad. However, as you get closer, you need to keep a few things in mind. The radiation near the black hole can be extremely deadly. The chances of escape get slimmer the closer you get. And if you get close enough, you now have to worry about being stretched into a giant noodle and time getting really weird. So, unless you have great radiation shields, a faster-than-light spaceship, or you're completely indestructible, you should probably just stay away. Well, that pretty much sums up black holes, at least before things start getting really complicated. But before you go for real, please refer to the handy brochure in your spacesuit pocket, since there's quite a bit to remember. Now then, remember your tickets, enjoy your trip, and please, be careful.
Okay, so how are black holes formed? It's a big question now, and we still don't understand clearly. But stellar mass black holes, definitely we understand how the star falls due to its own gravity, and it becomes more and more compact. So, for example, if I compress a human body, a human size, into the size of an electron, for example, it can become a black hole. So any mass can become a black hole if the mass to radius ratio is small enough. Sorry, the radius to mass ratio is small enough. So this is the essence of black holes. Nothing can escape. And black holes don't eat matter directly. It accretes matter because you see that the angular momentum around it. You have to lose angular momentum to fall onto a black hole. It captures you far away, but it doesn't directly. The cross section is so tiny for a black hole for any given mass. it doesn't gobble up directly. So always, almost always, black holes eat through accretion disks. There was a very, very big discovery in 2017, which I want to mention, that we detected gravitational waves from a neutron star merger. And this is a very big discovery because this is called multi-messenger. So what is multi-messenger? What I have been talking to you about all along has been the electromagnetic waves. I'm talking about optical light, I've been talking about infrared light, I've been talking about X-rays. All are electromagnetic waves, right? So it's one type of messenger. But there are other messengers, for example, gravitational waves. And for the first time ever, and to date it's the only time, we detected a neutron star merger followed by a GRB. A GRB means a huge flare of high energy events. You see that there is a blip on the top right where the GRB it's stated. So it's 1.7 seconds after the gravitational waves were detected. So you see the chirp on the bottom. You see something is going up abruptly. So that is the chirp. Chirp is the gravitational wave signal strength. And we see a GRB just after that. And this discovery has opened up a huge forefront of multi-messenger astronomy. Neutrino is also one of the other messengers of astronomy. And this is a genius in our field. I think everybody knows that about Hawking, and he was the one who proposed that black holes emit. By emission, black holes don't directly emit, but black holes can use up surrounding matter to evaporate. I'll not get into the details, but there are theories by which black holes, the smaller the black hole, the faster it evaporates. So this is a cartoon, so definitely do not believe that it's true, but this is true to the extent that we observe things and we believe it to be true, but this picture is cartoon. So this is how a not supermassive, it's a stellar black hole, is accreting matter as in a form of a disk from an adjacent white dwarf star. So this is a star which is giving up matter. And you see the jet is coming out as well from the black holes. Now, I'm not getting into a lot of things, but definitely some of my work is on the black holes outflows. The black holes just not eat, but also gives out a lot because the system is so energetic, it gives out a lot of things. So how do you measure all these outflows and things that are being thrown out? So there are lots of high energy particles being thrown out, and we measure it in absorption along the line of sight. So something which is absorbed along the line of sight and it's outflowing towards us with high velocity, it means it's thrown out by the black hole. And these materials are all rich with higher Z elements, which are higher elements, not just hydrogen, helium, but also carbon, oxygen. And these diagnostics that we see, so this is from one of my papers. These are the diagnostic features that we do. So although the science that you see is very fascinating that we do in the end, but the actual work that we do, the hard work, is as a scientist is kind of very boring, in the sense that you have to study all these absorption lines, fit the absorption lines, get the strength, get the nature of the absorption lines, do statistical analysis. And Professor Udara, he's my friend. I mean, he is an expert as well in all these things. And I mean, I'm sure in his talk he has mentioned all of these things. So we have to do a lot of these analysis to get to a point where we understand how the black hole is throwing things. And I mean, just giving you some examples of these things. So different black holes behave in a different way. No two human beings look alike, right? Even twins don't look alike. And the same thing happens with black holes. And no two black holes are same and they don't behave same. But what we do is a statistical analysis of many black holes and we see how they behave in general. So that's something which we do with human beings as well. So feeding the AGN is also AGN is active galactic nucleus. So I was mentioning about a supermassive black hole sitting at the center of the galaxy, and it is eating a lot. And the eating doesn't happen directly. I mean, it eats through in a certain way. I mean, suppose someone just gives you a food, you don't eat it. You have to wash your hands. You have to sit on the table or like sit on floor. You have to have a thali. You have to have a plate, and there are certain protocols that you have to follow before you can eat. So the same thing happens with black holes, that black holes just don't eat. So the particles that fall onto the black hole are captured first in an orbit around the black hole, and it cannot fall into the black hole unless it loses the angular momentum. So what is angular momentum? It's the moment, it's a moment of linear momentum. So I'm sure you're all science students, you know that. And unless you lose angular momentum, you cannot go nearer, 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 nearer. So you need to lose angular momentum. And for that, you need other particles to take away your angular momentum. So you need a uniform disk around the black hole where some particles flow in and some particles flow out. These outflowing particles are very important because they are enriching the galaxy, the host galaxy with, and that's what I was talking about, the outflows from the black hole system. The black holes don't emit or throw anything out themselves, but they have a central engine like the accretion disk and jets and all these outflows, which are powerful enough to interact with the host galaxy and in the universe. You'll not believe me when I say our own Milky Way was an active galaxy millions of years, I mean, I should say billions of years back. So our Milky Way was active and it emitted a huge amount of X-rays from the center. Still now it emits X-rays, okay? But that X-rays, when it was active, would have killed all of us. So it's good that Milky Way is not active anymore, and that's why human or life could be supported. But there are a lot of active galaxies, and we still want to answer. So how do you know the black hole is feeding? Again, we get back to spectroscopy. This is an important way. So when we see that there are dips in the spectrum and spectral turnover, and we know that obscuration is happening at some time scales, and due to the line of sight gas which is falling in, we know that the black hole is eating. So these are the different types of things, and we have multiple papers on these things. So there are many models, many structures that can actually help us understand the black hole is feeding. This is the last part of my talk, the second last part of my talk, where I want to mention about my recent discoveries, me and my team's recent discoveries. Changing look AGN are very, very, very fancy. So the recent discovery that we had in 2022 was from a source which became bright, an AGN with a supermassive black hole. It became bright by 100 times in a matter of 3-4 months, which is very unusual. I mean, there are other cases, but this has been very unusual. And like there are X-ray emitting gas clouds, corona, which is sitting very near to the black hole. The corona completely vanished at some point and it came back. And this led to a lot of papers, and our work was mostly related to the magnetic fields. So the magnetic fields in the accretion disks are very important in angular momentum transfer and also the accretion. So we think what happened was that this north-south polarity change happened, and this is the paper for which I got the award for NASA Exceptional Scientific Achievement Medal, and I will share a video for you to understand first. So where are you? Okay, let's see.
At the end of 2017, a galaxy 236 million light years away began a rare and dramatic transformation. It's an event astronomers are still puzzling over, one set off by changes near its central black hole. They first explained this as a tidal disruption event. That's when a star wanders so close to a supermassive black hole that it's torn apart. A new study of observations spanning the entire event suggests a different cause. The trigger may have been a flip in the magnetic field in the disk of material around the black hole. The sun's magnetic field reverses polarity every 11 years. On longer timescales, even Earth's magnetic field flips. Starting in December 2017, the galaxy began to brighten in visible and ultraviolet light. The source of this brightening appeared to be the disk of material around the supermassive black hole at the galaxy's center. It peaked 3 months later at nearly 100 times its previous brightness. That's when regular monitoring with NASA's SWIFT satellite began. As the visible and UV brightened, X-rays from the galaxy dimmed. By August 2018, the higher energy X-rays had disappeared completely. A few months later, the high energy X-rays came back, even brighter than before. They returned to normal within a year. These X-rays come from a cloud of super hot particles near the black hole. It's a feature called the corona, which is formed by the strong magnetic field. The lack of higher energy X-rays means that this structure was essentially gone. Based on observations from SWIFT, Europe's XMM satellite, and ground-based optical and radio telescopes, here's what may have happened. The visible and UV flare results when the flow of matter into the black hole increases. This may have started when the magnetic field in the disk's outer regions began to flip. The weakened magnetic field can no longer support the corona, which vanishes. The flipped magnetic field gains strength, restoring the X-ray corona, but the inward flow of matter is still high, so this emission is stronger than it was before the flare. Finally, the corona and disk return to their states before the flare, now with a flipped magnetic field. Rapid changes in UV and visible light have only been observed in a few dozen active galaxies like this one. But this is the first time X-rays have been seen to drop out as other wavelengths brighten. These surprising events offer a tantalizing glimpse at the extreme forces at work near an actively feeding supermassive black hole.
So
So that was a very big like a phenomena which resulted in multiple work. I will not get into the details of magnetic field inversion, and these were some of the figures which I have put these figures just to show you how detailed studies that we do with the data. And magnetic field inversion has been a very big event. And believe it or not, the same source is now showing a jet in real time, forming in real time. So these are the papers that me and my collaborator wrote, Mayer et al. 2025 and Laha et al. 2025. And we find a jet in real time coming out of this system of the black hole. And I'm again not getting into the details of the figures. So I'm trying to give you a glimpse of what astronomers do. So astronomers just don't make beautiful pictures. This is just the very final state of the way we want to convey the results. But the most important things are boring because these are all the figures, the plots, the error bars, the statistical analysis that we do, and all the hard work that goes into it. So a huge amount of, so this is a multi-year, you see it's on the x-axis, it's 2021 to 2025. We have been monitoring this source in multiple wavebands. In the top panel it's soft X-rays, in the middle panel the big one is the radio. And you see the radio has gone up by almost 60 times in just a few months. And finally, we see a spatially resolved radio jets coming out and at a speed of 0.2 C. This is a very big discovery because for the first time ever in the history of astronomy, we see a real jet, radio jet coming out from a black hole system. So on the left, on the extreme left, it's from June 2023. We don't see any extended structure. If you subtract the core, that is subtract the core of the central engine, there is nothing. But starting February 2024, we see a structure that is coming out, and it's evolving a lot, and it's coming out in a very nice way. So the jet, that the portion of the jet that faces us, in a way, it's Doppler boosted. It's more bright, and the one that faces away is weaker. And these are soft X-ray emission, which is very very high right now because the jet is being emitted. And this is again a cartoon of the jet, which we think was emitted when the soft X-ray was also rising. But initially we could not see the jet because it was hidden behind a cloud. And this cloud is it could be anything. I mean, mostly near to the black hole, but it could be anything. So all of these are discoveries, and we are going on with a lot of work now. And so as a Swift mission scientist, I'm working on many projects right now, and Swift satellite mission has enormous capability to detect high energy phenomena. For example, the gamma ray burst, which is a very bright burst from stellar systems. We see blips in high energy radio, and this is I took it from the website. So this is a Hubble Space Mission Operations Center at GSFC, and we have for Swift we have similar mission operations, and we monitor a lot of things, and we see that the spacecraft is doing well. Just a very recent result from one of my PhD students. He found enormous big data sets from one of Swift's telescopes, and he found that he could explore all these magnetar bursts. So magnetars are highly like magnetized compact pulsars. And these are stars basically, and they are high magnetic field, 10^12 Gauss. Sun has 1 Gauss. So you can understand 10 to the power 12, like place 12 zeros after 1. So that is the amount of magnetic field that are there, and these are pulsing and throwing out matters, and these are on the left that you see are the pulsings, and we are studying these light curves and time series. Thank you very much for your attention, and I'll stop there. Okay. Any questions that you have?
If you have any questions, the chat is open.
Okay, let me go through the chat. Okay. So if there are no questions, then thanks again, and it's up to Dara to decide the next action. So Are those jets from the black holes considered as so quasars are the systems of AGN. So it's quasars are the
Yes.
AGNs themselves.
So to go to
The quasars are AGNs themselves. So the central in the black hole, the accretion disk, and all these things consist quasars. So jets are coming from quasars. Quasars are very bright AGNs, and Seyfert galaxies are weaker AGNs. So yes, next question. Always I get a question when I'm giving a public talk, white hole, wormhole. These are all theories. There is, to my knowledge, there is no evidence of these in actual world or actual universe. So there are lots of theories like this. If they can be proved in future, that would be great. So theory is something which you can definitely you can propose a lot of ideas. That's good, but it has to be validated by observations. So this is a good question, how these massive black holes, TON 618 and others are created. So this is still a big question. I mean, how supermassive black holes are created is a big question because JWST has found that supermassive black holes of the mass of 1 billion times the solar mass, 10 to the power 9 times the solar mass, exists at a redshift of, like, say, I don't know, 7 or 8 something. So it means that when the universe was very young, that massive black hole was there. So it means that our theory of black holes, tiny black holes forming, and they are eating and getting big. That's the way the human beings happen. Like we are born tiny and then we eat and eat and eat and eat and then grow. That theory doesn't hold true. So that's a big question, and we still don't understand how and why these massive black holes have actually formed, and I mean, how are they like interacting with the host galaxy? So that's a very ongoing study. What happened? Can black holes die? Yes, black holes can evaporate, as per Stephen Hawking's theory, and black holes, as the smaller black holes, evaporate very fast. So I think it's inversely proportional to the time is inversely proportional to the size, the mass. What happens when a black hole enters a galaxy? Black holes, okay, there are instances where there are merging of galaxies, and you will not believe me that the stellar density in galaxies, although they appear very dense, they are not dense. They are very sparsely located. What happens when a black hole enters the galaxy? So most galaxies have a black hole at their gravitational center, and these black holes have been formed previous to the galaxy being accumulated. That's something which we think, or maybe, so which came first, the chicken or the egg? So which came first, the black hole or the galaxy? It's a big debate. What happens if a black hole comes into the galaxy? Of course, there will be gravitational disturbances because of the black hole, but there are merging galaxies. There are lots of studies going on right now. How much is a 1 minute on a black hole? That's a good question. So it depends on the black hole size. So the very massive black hole, for example, so if you go near a black hole and come back, the time will tick slowly near a high gravity range. So since this question has come up, let me give you a very interesting thing. You should go and look up Google. What GPS satellites which are in a low Earth orbit, which are in a geostationary orbit, which is around 35,000 kilometers from the surface. These GPS satellites are far away from Earth, okay? We are very near to the Earth. Now, our clocks are ticking slowly. GPS clocks are ticking faster because of this gravity difference. Now, we have to restart or adjust the GPS clocks every single day, if not every single month or year. For example, many NASA missions switch off their machines and then switch on with the proper timing. So this you should look up in the Google, that you can search by GPS clock correction due to gravity. So this is very important. You can see it in real time. Actually, this happens with us every time. So if you don't correct for GPS, this gravitational time delay, because of the gravity being strong here and gravity being weak there, after 10 years, maybe when you search for your home, it will show you like 10 feet away or like 100 feet away, something, because everything has gone wrong. So definitely high gravity, the clock tick slowly. And if you go to near a black hole and come back, near the black hole, your clock has ticked for say 1 year. And when you come back, it's again the dinosaurs have come back. So that can happen. Yes. Unfortunately, the nearest black hole is 3,000 years, light years from here. So it's not possible for us to go there. Okay, how much time? Okay, anywhere, any explanation that happens in no singularity, we don't know. What is spaghettification? Spaghettification is exactly what I was talking about accretion disk, because gravity is so strong between point A and point B. The gradation of the gravity, we call it the grad of gravity, is so strong that your legs have more gravity than your head. So you will be pulled apart like a spaghetti. And that's what happens when accretion disks are formed. What exactly is in a black hole? No one knows. Does time stop in a black hole? No one knows. So we don't have any concept of anything inside a black hole. So within the event horizon of the black hole, we have zero knowledge. You have to understand that. Why do accretion disks around black hole form a flat disk structure, not a sphere? Very good question. So it forms a flat disk-like structure because the sphere which is rotating around the black hole, for example, it will be many particles will be captured in different directions. So it should have been a sphere, right? But those materials have self-gravity within them, right? So they will attract each other. So after some point of time, the particles will attract each other and form a disk. And the interesting thing is that that disk may not always be aligned along the direction of black hole spin or black hole axis. So that is a very interesting thing that happens. In most cases, the disks are a little tilted. The disk perpendicular radius thing is a little tilted because the material that is falling onto the black hole has a self gravity. So there is a disk. It's not sphere. So what is the biggest black hole name? I don't remember. It's Ton something. How many black holes have now been? Oh, millions of black holes are there. So there are stellar mass black holes that are all over the place in this galaxy, and there are lots and lots of black holes. Why things entering a black hole gets frozen in the event horizon observing from outside? That is a good question because it's all mathematical right now, so we don't have direct evidence. So it's because we don't know how the space and time behaves within the event horizon. So suppose you are in a car and you are with a speed of v, and you know the acceleration, you can calculate where you will be in next 10 minutes or 5 minutes or 3 minutes because you know the motion, you know the equations. But for black holes, you don't have any information about anything, even time. But this time factor, time is completely relative. This is something which I really want to, at least if you don't take anything from this talk, just take one single thing, is that time is relative. And you should definitely go and look up Google for GPS time correction due to gravitational pull. So there are the differences in gravity between here on the surface and at that thing. So gravity definitely dilutes the time. So the time ticks slowly. Are black holes dangerous? If you call it dangerous, yes, of course, dangerous in the sense it will, suppose you're falling, I mean, just hypothetically, someone is falling from a 10-story building, they will not live, right? And now consider someone is falling from a 100-story. So even a tiny black hole will attract much more than a 100-story building. So it will be dangerous, definitely. What is the lifespan of a black hole? We don't know. It can exist unless it evaporates. If the universe is only 500, no, universe is not 500 million years old. No. Universe is 13.4 billion years. So, at that time when the black hole was formed, okay, that I now got it. At that 500 million years old universe, you get black holes of mass 10 to the power 9. We still don't know. That is a big question, because all the theories of black holes point to the fact that black holes eat matter, like accretes matter and grows. But how can black hole accrete so much in so small time? Now it gets to the theory of the steady state universe. Universe always existed. It's just like compressing and dilating. So what happens is, like, universe always existed, black holes always existed, galaxies always existed. It's just the universe is expanding now. It will then collapse, and then it will expand, and then collapse, and then, so that's a steady state theory that's given by Fred Hoyle and Narlikar. You should go and read steady state theory. That's a beautiful theory. Everybody rejected the theory because we don't have the proof for that, but we are getting proof gradually. What star did collapse to? I mean, stars don't just fall into black holes. I showed you the picture. They just accrete onto a black hole. Does black hole spin? Of course, black hole has 3 parameters. One is the mass. One is the spin, which gives you also the angular momentum, and the third one is the mass, spin, and I think is that as the temperature. So there are 3 parameters that black hole spin is very important, because that is also a source of energy that you can like use it to create jets. Quasi-star is a quasar that's it was named quasi-star because there was no better name. In 1960s, when people discovered that black holes accrete matter and they become bright, just look like stars, but they are not stars. That's why they are called quasi-stars. Did I answer all of them? Where are the supermassive black holes typically located? Okay, they are located in the centers of galaxies. Supermassive black holes, for example, our galaxy Milky Way has a supermassive black hole of 10 to the power 6 times the mass of the sun. So 1,000,000 times the mass of the sun. It's sitting right at the center. Gravitational center. What do you mean by center? Gravitational center of the galaxy. Does black hole emit any sound? No, because black hole doesn't emit anything. And also, like, sound is very much like if you want to convert some wavelength to sound, that is fine. But sound, the concept of sound comes when you are talking of a medium, and most of the universe is vacuum. So this is the thing. It says that the star called this collided to a black hole. Is it true? I have no idea. There are lots of news all over the place, but star coming and getting captured in an orbit in a black hole is very common. So it does not come and just face on collide. It's very, 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 very rare, because a star of a size of the sun, say 10 times the sun, the corresponding black hole size will be around, say, 30 kilometers. So 30 kilometers means a city, a size of a city. So this tiny thing and this big thing usually don't collide. So what they form is a binary system. Does every galaxy have a black hole at the center? Yes, we think so. We have so far, yes, we have seen. Could Big Bang be a black hole? Yeah, that's what Neil deGrasse Tyson was telling us. Could we be in a black hole? I don't know. I mean, I have no idea about what's. I mean, he used some circumstantial evidences to say that we are sitting in a black hole and the Big Bang is actually a black hole. We don't know. What is equal of Earth? I don't understand the question. What is the largest black hole found up to now? That's what I told Ton something. You can get that from Google. Is there a black hole named Sagittarius A star in Milky Way? Yeah, of course. There's that. That is the main supermassive black hole at the center of Milky Way, and that's 10 to the power 6 m sun. That is 1 million times. Sorry, yeah, 1 million times the mass of the sun. If time stops near the event horizon, wouldn't we see the accretion disk rotating at the event? We don't see anything at the event horizon, to be frank. We see everything out of the event horizon. So accretion disk or whatever we see is out of the event horizon. We don't know if time stops at the event horizon. We don't know anything about time and space at or below the event horizon. So it would be injustice to say what happens to time there. Are black holes dead stars? Yeah, in a way, it's a dead star. Dead, but like active in some other way. If black holes are the ultimate gravity wells, do they swallow dark matter? That's a good question. Dark matter, the nature of dark matter is yet not known now. We only see things when it's a visible matter, like the baryonic matter that we see now. About dark matter getting into black holes, that's an open question right now, but a very good question, I should say. How large a black hole can be, that's no answer because it can be anything. Are black holes wandering freely in space? That's a good question because, I mean, by wandering, you mean moving forward. Yes, like there are systems where what happens is the collisions between two galaxies and massive black holes happens in a way that one black hole is flung out of that galaxy and it just moves away like a ball. And there are evidences of these things happening, but black holes are too tiny for a given mass. For example, this Earth, if you convert to black holes, it's just the size of a coin. So it's too tiny to interact. In any case, the space is mostly vacuum. Even in galaxies, the density of the stars is very, very little. So even if a black hole passes through our galaxy, yes, we will definitely be able to see some commotion, something, but it will not be able to disrupt the entire galaxy. The galaxy will still be there. Are there black holes wandering freely in space? What do scientists think happens when to what are swallowed by black holes? So I told you this the three parameters we have. We don't know what happens when it gets into black hole. It's that the black hole mass becomes more. So for example, suppose I throw a stone at a black hole of mass m1, and if the black hole has mass m0, then the total mass of the system will become m0 plus m1. And if there is a spin or if there is a temperature, these will be different. Who discovered black holes? That's a good question. Chandrasekhar proposed that black holes exist. And when he proposed that black holes exist, he was just 21 years old. And he calculated that. And Arthur Eddington, who was a very famous scientist, he became so angry, he told that you don't know anything. And he actually made it sure that Chandrasekhar doesn't work in UK anymore. So Chandrasekhar, out of frustration, left UK and went to Chicago University in US. And later on, black holes were discovered observationally through quasar systems and other systems. So there is no one person who has discovered black hole. A black hole eating our galaxy? No, black holes don't eat. I told you black holes are not vacuum cleaners or like directly eating. They eat very slowly. The accretion disks are the only way they can eat. Information paradox and how does it relate to black holes? I don't remember exactly. I mean, I don't remember exactly what is that. I mean, there are like other paradoxes, like a brother sent to the black hole and came back and he became old, and another one is young. So there are lots of paradoxes with black holes because the black hole system, we don't understand very well. Can planets be black holes? I don't think so. I told you anything less than the mass of 1.44 times the mass of the sun cannot become a black hole. What will happen if two black holes collide? Of course, two black holes collide very often. Gravitational waves, we see a lot of gravitational waves. Since black holes don't have baryonic matter, that is the visible matter that we see now in terms of the Mendeleev's periodic table, I mean, they don't emit electromagnetic waves. So nothing visible or electromagnetic is seen, but we see gravitational waves constantly. There are lots of black hole mergers happening. Why we see supermassive black holes in the very early universe? How did they get? So if you can discover how did they get so big so fast, I think a Nobel Prize awaits for you. I mean, these are brilliant questions, I must tell you, and you should pursue these questions in your research, in your further work, and in so now information has become readily available, and in your research, if you want to do research with your colleagues and with your teachers, these type of researches can make breakthrough discoveries. Is there end of black hole? Yes, we think so. What's the speed of black hole? There is no speed of black hole. How many light years is the closest black hole? 3,000 light years. Does a singularity actually exist, or is there a tiny ultra dense physical object like a Planck star at the center that we just can't see yet because we haven't unified gravity? Wow, this is a very good question, very heavy question. I'm amazed with this question. Thank you for this. Yes, it can be the case. So now I'll tell you. Singularity is a mathematical limitation, and we have not yet, our mathematics has not yet gone to the point that we can deal with singularity. And the problem is that the singularity that we commonly face is the division by zero is can only be gotten rid if we have a different set of mathematical formulations. So everybody should understand one thing. I don't know if you're taught this in school. Mathematics is based on axioms. So you have a set of axioms which you think holds true, and based on that we develop mathematics, and with a lot of and then the mathematical rules come in, and then we see that it works in our daily life, it works with observations, so they're true. So we have to get back to the axiom stage. That okay, so for example, I'll give an example. The example will help you. So in early 1900s, so 1900 to 1905, there were great mathematicians like Lorentz, Poincare, and Helmholtz, and all these people. So they were trying to understand how to how to define relativistic speed, like if something becomes very very high speed, and how they were confused with relativity actually. So how to write the proper equations for relativistic speed, and if a mass moves at relativistic speed, how do you define relativistic speed? So it is Einstein's genius that he assumed two things. Einstein did not prove two things, he assumed two things. Again, I'm telling you, Einstein did not prove two things, assume two things. One is that nothing can travel faster than the speed of light, c. So that is an assumption, that is not a proof. The second thing he assumed that so again, I'm forgetting the second assumption. So there is another assumption which says that the speed Yeah, so I think it relates to mass. So if you just look at the special relativity book, there are two assumptions that Einstein made to propose his special relativity. Okay, he combined space and time. So sorry, I'm so sorry. The thing is, the space and time are two distinct objects in Newtonian theory. We always think like, so you're sitting here on a table and you think this is space, and the watch is giving you the time. So space and time are two different things. He told that these two things are not different. He combined space and time, and he assumed that c is the maximum speed achievable by any signal. By any signal means any signal. And that has been proved that the gravitational waves also follow this axiom. And gravitational waves, so the discovery I showed you with the GRB, when two neutron stars merged, we found that the signal that came, electromagnetic signal, gravitational wave signal, um, had exactly the same speed to the ninth decimal place. So Einstein assumed these two axioms, and on that he built his entire huge theory of special relativity and general relativity. So to answer your question, I'm sorry I took a long time. To answer your question, how to deal with singularity, and if we have to get back to axioms, mathematical axioms, and redefine the axioms, reassume the axioms to get to a better. Um, Planck star, you can just look up what is Planck star, Planck length, Planck star, all these. So what is supernova? I will not get into these because these are very standard Google questions. When Andromeda galaxy collided with Milky Way, will the supermassive black holes centers? Yeah, the supermassive black holes will not collide, but they will have a mutual angular momentum, and there are galaxy dancing. So the galaxies will be around each other for quite a long time. Sir, can you give me the picture of a black hole? Picture of a black hole you can get, just search for Event Horizon Telescope discovery of black hole image 2020. I mean, there has been quite a few images. So just look at that. So that is the real image. Not image, it's the shadow of the black hole. So you can get it from the Event Horizon Telescope, EHT. Can the Great Attractor be a supermassive black hole without a host galaxy? I don't know. Can light enter a black hole and can light escape once it passes the event horizon? No. Can a singularity without an event horizon exist? I mean, event horizon is the boundary of singularity. I don't understand the question. When two black holes collide, does the process appear slower than before due to stronger gravity? Yes, of course. Nearer to the gravity field, time ticks slowly compared to an observer outside. And again, I'm repeating, please go and look up at Google. Why do you need a GPS time correction? I mean, GPS satellites need time correction due to gravitational. There is a microsecond delay, I think, per day or per month, something like that. So we need to correct that delay because of, I mean, we are ticking slower, they are ticking faster. Okay. If black holes have such strong gravity, not even how do scientists detect and okay, black holes. So detection of black holes is all circumstantial because we cannot directly detect a black hole, right? So, but we detect all the matter around it and the energy that is being emitted, and so we detect it indirectly through the accretion, and we apply physics and we see that nothing can do that except for a very compact massive object. So please give answer, what is supernova? Supernova is nothing but a star that bursts because of its own gravitational pressure. So there is a core which is very highly dense, which can be a neutron star, and the outer core just bangs onto the inner core and just bursts open. So you should definitely look up what is supernova. There are like loads of information, loads of video on supernova. It's a common knowledge. Mass energy conservation, yeah, that is also a fallout of, so mass energy conservation is a fallout of his axioms. So this is a very, of course, very important, um, like a theory. I mean, it's not a theory anymore. It's actually it's a law. Please give them is a black hole and combiner air. Air is something which you see around you. So these are all particles of different types of gas molecules that are around you. Space is a vacuum. Space is mostly vacuum. So has space air? No. Space doesn't have air. Unless like you are in a nebula which has some type of density in terms of electron and hydrogen density. Yes, we calculate densities, but technically not air. Air is a different composition, and we don't have air uh, outside of the planet. Are black holes exist till the end of the universe? Don't know. We don't know even what's the end of the universe. Who took the first photo? The first photo of a black hole was taken by EHT, Event Horizon Telescope. That's a brilliant marvel of human engineering. Is there a similar planet called Earth too? I don't know. If you know, tell me. That would be good. I think I answered all the questions. Will you give 5 more minutes for your questions? I have a meeting at 11:30, which is 11:26 right now. I'm glad you're asking very good questions. Are you enjoying the answers, or I'm not getting any feedback? Like, are you getting the answers, or are you getting any answers, or like you? Anyway, so I'll just answer a couple of them and I have to leave. Actually, what is simulations? I don't know about what you mean by simulation theory, but we simulate events which we want to see in observations with the physics in computational mode. So we write codes, we write all of these things to simulate certain situations and see what happens. So simulation theory is not a right term. We simulate different observational things to validate or to augment our theory. So simulation is an important aspect of our investigation. Very, very important aspect of our investigation. Is the black hole a 3D object or a 2D image? It's definitely a 3D object because you saw the jets coming out in 2 directions that we discovered last year. So definitely it's a 3D image because it's all dimensions in 3-dimensional space, unless you discover like 5-6 dimensions. What is the biggest black hole? Okay, that's something. What happens when air gets released to the vacuum of the Earth? I don't understand. I mean, you mean the air just goes out of the Earth? So Moon also had air, if you remember. So Moon's air is gone because the gravity is not enough strong to keep it bound to Moon. I mean, the thermal speed of the Moon was more than the escape velocity. So the air went away. For Earth, it's not the case. I mean, if it goes away, of course, we'll not live, but what will happen is that the air will be into the vacuum and it will just float away. Just that will happen. Okay, so I think that's all. It's 11:28. So if there are no questions, then thank you very much. And anything that you want to say? Yes, tell me.
So thank you, sir. I would like to give a special word of thanks to Dr. Subhashish Laha for delivering such an insightful and inspiring lecture today. Representing NASA, your contribution has added immense value to the Galileo Troop, and we sincerely appreciate your commitment to supporting this island-wide initiative. And once again, I'd like to express our sincere appreciation to Dr. Anushka Udara for gracefully moderating and supporting today's session. And thank to all the participants who joined with us today with another valuable lecture. Hope to meet you soon. Representing Anandian Astronomical Association, I'm Lucky Ravanasingh. Good night.
Thank you.